Okay, thank you very much. Good morning, everyone, or whatever day you happen to be in. So yeah, I'm going to be talking today about gravitational wave observations, and I apologize that I haven't been able to follow all the talks that have happened. So I hope I don't go over again too much what folks have said before, but what I did want to do is spend a little bit of time today, given that it's a summer school environment, giving you a high-level conceptual overview of gravitational waves in general, sort of an astronomer perspective on the energy scales involved and the length scales involved and how those are connected, and talk a little bit, again, given the time, not in any mathematical detail, but some of the concepts that lead to us being able to measure the tides. I'll talk a little bit about the results from the LIGO and Virgo collaborations observations so far, and a little bit about where the potential places we might be going next. So I'll get started. And unfortunately, if I want to share my video, I can't see anything in the chat. So I'll just assume everyone's going along fine. So this is the one minute introduction I usually give to gravitational waves. And so fundamentally, we know that gravitational waves will come out of a relativistic theory of gravity, because if the curvature of space-time changes around something that's moving, a distant observer, unlike in Newtonian gravity, cannot instantaneously know that that has happened. So the change in the curvature of space-time, which carries gravitational information, has to propagate out at the speed of light. One way to see this is if you take Einstein's equations of general relativity and linearize them, you recover a wave equation that's very similar to the wave equations you would get out of Maxwell's equations in electrodynamics, just with a few extra complexities. And then we also know that not only do gravitational waves not only are they emitted from binary systems, but they can have effects on the objects that they pass through. So the stretching of squeezing of space that comes out of here, these possible images of binaries, alternately stretches and squeezes the distances between freely falling objects in a transverse direction to the propagation of the wave, which you can see in the lower animation here. So how I wanted to go back even a little more and talk about how you can see some of the structure of the sources of gravitational waves from a base fundamental understanding of gravity. So to start off, if you're floating in space, by the principle of equivalence, everything is affected by gravity in the same way. Everything falls together. So if you're, isolated in your little laboratory elevator here, even if you and your elevator are falling in a gravitational field, you won't be able to notice any effect of that unless you have some differential gravitational effect. Okay. So the effect that we experience from distant objects that's gravitational is not the falling as much as the tide. So locally, what we notice due to the gravitational effects of distant objects are tidal fields. They're gradients in the gravity, the gravitational acceleration here, that are different in two different locations. Here, sort of schematically, these two baseballs in our lab elevator each have a slight different angle of gravitational pull to a distant mass. And that gives a gravitational gradient proportional to 1 over r cubed, even though the force is, as it is in electromagnetism, proportional to 1 over r squared. So this is what gives us, say, the tides on the Earth from the moon. Okay. But now, let's launch our gravitational source into action. And what this is going to do now I'm going to go back to this electromagnetism analogy that I've been making and talk about how we think about gravitational radiation in a way that can be mapped onto how we'll think of gravitational radiation. Okay, so you start off, you have a monopole, a collection of charges. There's an electric field that scales as that monopole over r squared. And if this collection of charges is far away and varying in time, you can express it in terms of this time lag potential and find a find an electric field that's a time derivative over r. So we've got a time derivative and a r factor coming out of this expression. Okay, now of course, charge is conserved. You don't have monopole radiation. So when we're talking about electric fields that radiate, what we end up going is to the next order in a multipole expansion of the charges source distribution, which would be the dipole. This, from the properties of expanding in monopole, dipole, quadrupole, and so on, we get, again, a faraway source varying in time, a time derivative and a factor of r, repeated. So you have a collection of terms that come out of your wave equation from electromagnetism that show you that the leading order dominant contribution from a changing dipole is going to come from, for gravitational, the dominant contribution to electromagnetic radiation is dipole radiation coming from an accelerated dipole charge. Okay. So how is this going to happen? How is this going to play out for gravitational radiation? So again, I'm going to start with a monopole term. I'm going to be looking at the measurable effects of gravity. So we need a gravity gradient to be able to observe this without an external reference. The same procedure with a very similar set of equations can show you that the gravity gradient can be sourced by time-varying masses, well, except there aren't any. We have mass conservation, just as we have for charge conservation. We can do the same thing for the dipole. This is all just schematically equivalent radial dependencies to the form of the electromagnetic radiation equations. We see, again, a set of terms that for the dipole are proportional to mass times acceleration, summed over all the components of the source. And from our Newtonian idea of conservation, we know that there's no dipole radiation. And then finally, this is the kind of punchline of these couple of slides is to say that what is going to generate gravitational radiation is going to be a dominant source from some set of moving masses in a distant astronomical system. It's going to be a quadrupole, which this should be a proportional, this should be a proportional of m s cross s. It's actually a tensor term, not the same as the dipole on the far left there. So there's two powers of the radius there. That's one higher order in the multipole expansion, so it's 1 over r4. And then when we go through the similar procedure of expanding out terms and finding the leading order term, it will be the one with a coefficient proportional to a fourth time derivative of the quadrupole moment. And this is going to be the gravitational gradient that is driven by the radiation of a different distant source. Okay. I'm going to press on. but at the end, I'm happy to come back to these pages and sort of go through some of the steps that go through this. The first thing we're going to do, though, is say we're starting here in the middle with just the same gravity gradient proportional to quadrupole derivative before. And so what is a quadrupole moment going to look like? We have some mass moving in the different system. We're going to assume it has some characteristic oscillatory frequency. So those time derivatives are just going to pull down powers of the frequency 4 times. We have some distance size scale. This is coming from the quadrupole, has 2 powers of the source dimensions in it. And then the radiative component, as usual, is 1 over r, the dominant radiation term from a distant source. So what we end up here is that the gravity gradient is going to scale like the size of the source squared times the mass of the source divided by the wavelength of the gravitational radiation being emitted and the distance to that source. What this will end up doing, if we have, say, some test particles, we can take the relative acceleration of those 2 particles, do a couple of integrations to get their relative change in distance, put that into, or rearrange the gradient term to say that the change in distance relative to the distance between 2 particles is going to change in a way that's proportional to 1 over the wavelength squared, but again, the scale of the object squared, the mass of the object, and a 1 over r term. Now you can recast this to get a meaningful gravitational wave. What you'll want is for the motion involved of the source to be comparable to the speed of light. If the source is slowly moving, it will be very challenging to get a significant strain that's measurable from a distant source. You also are going to want to have a mass that is relativistically large. They have the g over c squared term there for gravity, which is a weak force. You'll need a large m there to get something potentially measurable. And so just rewriting again from the previous slide, the scaling we get out here, I've added a little subtlety here that the velocity that we end up being sensitive to is only the velocity that's parallel or perpendicular to your line of sight to the object. So any back and forth motion will not affect the gravitational field ripple that you experience. It has to be something moving to figuratively pull you to one side or another, not directly, but through the propagation of the gravitational wave. And you get scales of motion where the relative change in distance affected by the gravitational wave is order 10 to the negative 21 for neutron-star mass scale sources that are moving, that amount of mass is moving in a, say, if it was in a Keplerian orbit at a separation of the Schwarzschild radius of the objects. That gives us 10 to the minus 21 for feasible astronomical distances. So you can see that 10 to the minus 21 is the reason that the gravitational wave instruments are so exquisitely well engineered to measure that kind of tiny length change over a few kilometers of distance. Okay, but all this talk about the small effect of gravitational wave doesn't really adequately convey the amount of energy that's being carried by these very tiny ripples. Okay, so you can show that the energy carried by the gravitational wave is proportional to this h squared. You'll have to integrate over this the sphere as it goes out in all directions, and you can see that the luminosity of whatever system is kicking up these gravitational waves will be, again, kind of proportional to the amount of mass that's in motion and the compactness, the size of the system, the characteristic distance scale over which the mass is moving. And then some factors to make it dimensionless, take it to a fifth power, and then put it in units of luminosity. I can recast this in a few different ways. The one on the far right here shows that we have, again, something like something that is coming out of the comparison of the velocity of the motion to the speed of light and the compactness of the system to the Schwarzschild size, the most compact possible size before that defines collapse to a black hole. And you'll also get a characteristic time scale from the loss of energy due to gravitational waves as some fraction of the energy available in the system. Is sort of characterized by the kinetic energy of this mass and motion. So to pause from the math a little bit, this is how this plays out visually. So you, looking at your screen, can see in some distant system this time-varying mass quadrupole, and you're holding up your ring of particles with your gravitational wave detector in it in front of your face, and it's responding after an appropriate speed of light time delay to the distant motion of the astronomical system with this characteristic frequency. And so you can begin to see how observing the pattern of gravitational wave ripples is going to allow you to track the dynamics of the source system that's generating your signal. Okay. So back to the order of magnitude scaling, if I put some numbers into the luminosity characteristic of a binary orbit, the first thing that drops out is that the shear scale of this is something like 10 to the 59 ergs per second. This is orders of magnitude higher than, I believe, the summed output of electromagnetic luminosity of all the stars in the universe. So this is a huge amount of coherent energy being emitted by a compact binary system. And this is can be in turn carried away to, or inverted, or let's say it can be in turn applied to determine how that binary system is itself affected by its gravitational wave energy loss. So the separation S of the two objects over time is going to be determined by a sort of a physicist style ratio of two derivatives to get the derivative ds dt, and that's the gravitational luminosity related to the energy of the orbit, which at leading order you can just plug in your good old Newtonian kinetic and potential energy, and take a derivative with respect to the separation, and then plug in your leading order gravitational wave luminosity, and get a frequency of the gravitational wave tracking the frequency of the orbit that increases over time. The amplitude of the gravitational wave can also increases over time. And so this is just an example of neutron-star masses showing that by the time, say, they get to 400 or 500 hertz of frequency, the orbits are taking fractions of a second, which you can figure out from the inverse of that kind of frequency. The separations are around 60 kilometers, which is becoming comparable to the length scale of the objects involved. Now, the point, though, of this talk is to understand where the properties of dense matter that you've been learning about in the school, primarily in relation to things like the equations of state and the neutron-star radius that comes out of the hydrostatic equilibrium, how is that going to play a role in the orbital dynamics of these systems we want to observe in gravitational waves? So let me step through this slide here. So again, we're back just in Newtonian interactions. This is a calculation to give you an idea of how tides are formulated that can also be used to study the cracking of the moons of Saturn or Jupiter as they go through time-varying tidal potentials. This is a framework that's used to understand the motion of satellites around a non-perfectly spherical body, like most of them are. So if you have a non-spherical body, like we often do in physics, you can characterize its shape by a series of moments. And the quadrupole moment is going to characterize the gravitational potential around a deformed body. A dipole mass moment is just a shift of the center of mass, so that's not going to play a role here, again, for related reasons. But the gravitational potential here, we again have a mass piece and a quadrupole piece that are proportional to the angle away from this, the orientation of the particular deformation we're talking about. Now, as soon as you have as soon as you're looking at the gravitational effects from a deformed body, you can determine this Q from the size of the object, and then the Love number, which characterizes how the mass is distributed within the deformed body. So at a given orbital separation, you'll have an external tidal field from the mass of the companion body, and you'll get the size of a quadrupole deformation induced proportional to that external tidal field that comes from these characteristics. So although I introduced this idea in the Newtonian framework, we can apply it in a relativistic star. They'll take an equilibrium configuration that you would solve the relativistic Tolman-Oppenheimer-Volkoff equations for a cold equilibrium star. You would perturb it to look at its linear deformation, and this linear perturbation will have a quadrupole piece, an external tidal, a piece proportional to an external tide, and the ratio between them will be used to define tidal deformability. For gravitational wave analysis purposes, we often put this in a dimensionless form. It's just a little more straightforward to work with in some of the common applications. So we just scale by the mass of the star involved. So the radius and the mass of the star drive the equation of state's impact on the tides that are affecting the orbital dynamics of the system. But there is this Love number too, which has a significant role to play. It's not raised to the 5th power, but it does have an order of a few variation between equations of state. This again is characterizing the mass distribution within the star. If this is really interesting to you and you're like gauges, you can also read this archive link, because as often in relativity, the kind of Newtonian motivated treatments that I've introduced here can have some challenges when dealing with something as dynamic as general relativity. Okay, so we take again, an equation of state, and I think you've seen this for stellar structure before. You can solve hydrostatic equilibrium and get radius for a range of different equations of state. You can also solve perturbed hydrostatic equilibrium and get tidal strength for various equations of state. And then the only piece left to do is to take that tidal deformation and consider how that is going to affect the evolution of the system. I'm sorry, I just realized I've changed notation a little bit from the last time I had this equation. There's just entirely too many radii involved in these analyses. And then, so you take the ratio again of the gravitational wave luminosity and the derivative with respect to the orbit, and then you add a little extra luminosity from the induced quadrupole of the tides, along with the energy loss to deforming the star. And this is a subtle effect, most clearly visible in the final orbits of the merger, but induces a small shift that accumulates from sort of that accumulates. And you can see how this comes into play if I would just write down for you the formulation of the frequency domain expansion of a gravitational wave. So we have our strain as a function of time, something like the version I've plotted here. It's an oscillatory function, say with increasing frequency and amplitude. But we observe, or we work with our data primarily in the frequency domain. And so you can see, well, how does the amplitude and the phase evolution of the frequency domain version of this come into play? We find that the amplitude comes from this chirp mass, this squiggly M here, and the luminosity distance to the source. Q is a set of parameters that depend on the sky location, the angular inclination of the binary. Fall off with frequency once you're in the Fourier domain, once you're in the frequency domain, because at high frequency there's very few orbits per frequency bin, so the amplitude begins to decrease, even though in the time domain the amplitude is increasing with time as the frequency increases. The phase evolution, though, is where we measure the dynamics from the binary system. And so the phase evolution has some constants, and then it has an expansion in terms of this frequency parameter U that includes terms that are proportional to the mass ratio, here written in a dimensionless form eta, proportional to spin terms beta and sigma. You can begin to see here why, when we measure the properties of our sources, it's often there are often couplings between our recovered spin parameters and our recovered mass ratios. They're coming in the same set of frequency coefficients. And then way up here at high post-Newtonian expansion order is our tidal term. And well, if you're used to thinking about post-Newtonian expansions, you may worry that this means that the tidal term is insignificant. When you look at terms of the ratio of radii involved in the problem, this tidal term here ends up being proportional to the radius of the neutron star and the separation of the binary to the 5th power. And when these two become comparable, this formally high term in this expansion framework ends up driving the dynamics of the system. And of course, if you look at orbital interactions of non-compact objects, of course, you see that the tides are going to play a significant role compared to higher order corrections of relativistic type. So, you know, if I look at the Earth and the Moon, definitely need to worry about the tides before I'm worrying about any high post-Newtonian expansion in this kind of term. Okay. So let me just flip the order here. So what we, actually no, go back to the original order I planned. So what have we measured so far from these in-spiral signals? So cumulatively, the observing runs so far, where the rate of observations is roughly proportional to the volume of space that's accessible as the detectors have improved, we have now 67 total binaries that have been observed or alerted. And for O3A and B, there's some of these alerted events are under current investigation. So in O3A and O3B, our real-time rapid pipelines classified some of these as interesting, more likely to be things like black holes and neutron stars, and neutron-star black hole pairs. Then if you look at the masses recovered by mapping the gravitational wave signal to that expansion and recovering from the coefficients that best fit the observed frequency change in the oscillation measured in the data, we see that the gravitational wave from compact binaries are revealing some interesting new masses, both more massive black holes and have been observed in electromagnetic radiation before LIGO became functional, as well as neutron stars, and some interesting objects here in the middle, which are somewhat unclear in their classification, because the gravitational waves cannot always distinguish tidal effects of, in particular, when the masses are large in the system, that suppresses the tidal contribution to that signal, and it can become obscured by the background noise fluctuations in the detector at the time of observation. So these question marks there are so-called mass gap objects, where their classification is not clear. So let me play the sound. Okay, so let me talk a little bit about 170817, the first gravitational wave event identified on August 17th, 2017, which is yesterday. For me, maybe 2 days ago for you. Anyway, so a timely celebration 3 years ago, roughly from today. The first thing I wanted to do was go through, here's the data from the detectors showing the frequency as a function of time over the last 30 seconds or so before the two objects chirped up in frequency and merged and were lost to view from the gravitational wave perspective. So what do we actually observe here? So this, I've been talking about how these gravitational waves are tracing orbital dynamics of the source system. What are the orbital dynamics that are driving this thing? And I'll hop over into the frequency domain. So this here is the last, say, 30 seconds. The frequencies are going from approximately 40 hertz up to several hundred hertz here. So here we have the amplitude of the Fourier domain of this frequency with a particular frequency scaling between around 10, 100, 1,000 hertz. And this is the amplitude of the gravitational wave signal compared to the amplitude of the background noise fluctuations at the same frequency in the detector in Livingston that day, and where we're aiming for with advanced LIGO and Virgo designs. So 40 seconds before merger, the two objects were around 300 kilometers apart and had a gravitational wave frequency of about 30 hertz. 5 seconds before merger, they hadn't gotten all the way that far through this frequency plot. They were at a frequency of 70 hertz and an orbital distance of 190 kilometers. It was until the final quarter second that we got out of this sort of, well, we're just still in the bucket, so to speak, the most sensitive frequencies of the gravitational wave detector. And I apologize, the next part of the movie is not going to propagate through Zoom well at all. It actually doesn't even show up in the the YouTube video or the screen video because it's just too fast, even slowed down 80 times. But what we're going to see for this final stage is the objects sweeping together from 90 kilometers apart to contact from around 200 to 1600 hertz. And they contact each other coincidentally roughly at the time that the background noise fluctuations are rising up to swamp the gravitational wave signal, which limits the amount of information we're able to pull about into this because the tidal effects only come into play for these final quarter of a second or so and are the strongest in the final regions. Now these different colors here are numerical simulations with different equation state models, sort of showing how the different equations and state models affect the amplitude of the gravitational wave. We really measure the phase, so this is a useful illustration. And the bottom two are disfavored actually by the data of 1708-17. I can also mention that there's this post-merger region, so you see a lot of interesting structure, unfortunately buried in noise for 1708-17. We place limits on what might have happened after the stars collided, how much energy was released, and I think Paul Lasky will be talking about that later in your school. So stay tuned for more information about where that might be bringing us. But just to sort of highlight, so if you really want to go past the leading order types of calculations I've been showing, our real understanding of these systems relies on high order calculations and numerical simulations as the stars approach each other. So these final 40 milliseconds or so of the in spiral, and then the first or only perhaps 40 milliseconds or so of so far not directly observed post-merger and eventual collapse to a black hole. These final stages are important for understanding the real dynamics of the system and would require more than I can comprehensively cover in this today's class. I should also mention that there is a second observation, 1904-25, which had notably higher masses than our first one, higher than any binary double neutron star observed in the galaxy. And from our modeling of 1904-25, we expect that unlike 1708-17, well, there's a couple differences when the mass increases. So you'll see that the two stars here are less distorted by each other. The more massive stars are a little more compact and harder to disrupt, and they may just collapse lightlessly to a black hole without a lot of post-merger activity or electromagnetic counterparts. But as I mentioned, this was rather interesting in that, unlike 170817, which sort of lay smack dab in our known population of double neutron stars in the galactic systems, it's somewhere up here far away with a large total mass. So, and then the other final sort of background piece that I wanted to highlight was that if we really want to understand these final orbits where the gravitational wave signal for tides and thus the dense matter is strongest, we're really relying on sort of a double-pronged approach to understanding the higher order dynamics of the system, which includes full general relativity, discretized and simulated on a computer. This is at least until the merger, more or less tractable. It's difficult to resolve the changing pressure and density scales of neutron stars in numerical simulations, but we have a reasonably good handle on it. We describe these waveforms up to the merger as a function that you saw the simple expansion before, but there are more sophisticated models that are actually used for the analysis, but they do relate back to the component masses of spins and the component tidal deformabilities as defined in a linear perturbation. We can do this in two ways. We can either take a binary black hole model, add the tidal phasing from that leading term, and some phenomenological higher order contributions from numerical relativity calibrations. And there are also, in parallel, several theoretical programs designed to analytically compute order by order the effective gravitational interactions and tides with higher order terms, resonances, dynamical tides, things that are implicitly involved in the numerical simulations, but can be step-by-step worked through analytically in different frameworks. So you can see the results for our measurement for 170817. I'm showing here the posterior distribution function for the recovered tidal parameter. Here it's a particular weighted combination of the component tidal deformabilities and the masses that's the leading order coefficient in that big expansion. And depending on the waveform model that you compare the data to, you will get best fit parameters that can shift around a little bit. You see that the two black hole variants with numerically calibrated tides. We can just do a pure perturbative model that's compatible with known, pardon me, that's compatible with known simulations and frameworks, and then these analytic frameworks. And they're all relatively compatible, in particular, if we restrict the spins that we're willing to consider. So the spin sector modeling is actually, I wouldn't say exactly contaminating, but complicating the analysis of the tidal parameter as well, just because of correlations between the various parameters or source properties that characterize a gravitational wave signal. We can map in turn these observations of the tidal parameters to the underlying equation of state. And something nice here is that if you put this, say, in terms of pressure, the function of density, you can compare this to some previous work that was done entirely using X-ray observations and combining multiple X-ray observations in this sort of gray and blue shaded regions. The green is the gravitational wave analysis, and there's some different ways to formulate that, and they are all providing a consistent picture with relatively wide error bars so far, but a consistent picture of what the equation of state of neutron star matter can be. Okay, I think I'm going to wrap up here. Since there's time, so that there will be time for questions, I'll just say 1904-25 was uninteresting, and that based on our observed rate of neutron star mergers, we are on track to be measuring something like 40 per year based on the rate we've observed so far and the anticipated goal sensitivity of the LIGO and Virgo networks. So I'll stop there so I have time for questions. Thank you.
Thank you very much, Jocelyn, for an excellent talk. So I'll now go to the chat box and read out the questions in the order that were posted there. The first question is actually from the YouTube live stream. And the question is, I guess regarding one of the earlier slides, how does the ring of free particles that you showed get affected by gravitational radiation?
Right, so let's see. Please bear with me while I attempt to navigate while zooming at the same time. So I think I'll assume this ring of particles. Well, I guess this is the best answer I can give to that. Sorry. So the gravitational radiation, actually, as it travels, let me play that here. This animation in blue, you can consider these red particles as a free-floating ring of particles that are experiencing relative motion due to the influence of a gravitational wave propagating through space-time. So the gravitational wave propagation carries this distortion, the stretching and squeezing through space, and perpendicular to the propagation of the wave, the ring of particles is stretched and squeezed, as shown here. There's this rather nice, einsteinonline.info has a rather nice treatment of that. Should I move to the next question?
I was unmuted, muted.
Oh, sorry.
Okay, so the next question is, why does the tidal force affect the post-ring down object? Is it created during the in-spiral phase only? And a little bit unrelated question, is there any effective one-body approach to incorporate the tidal force?
So yes, the effective one-body approach is exactly what I was talking about with these semi-analytic component models. So the two references by Nagar et al. And Hindra et al. There may be some more recent work too that I could update this slide with, but these are effective one-body gravitational interactions, plus analytic tides, higher order terms, resummation, all the goodies of effective one-body motion. And so that is actually some of our gravitational wave analysis does use those methods. Now for the tidal force affecting the ring down object, I think the thing that I might say there, it's, well, so the post-merger, how does the tidal force affect the post-ring down object? I'm sorry, I don't quite understand.
I'm not sure. I'm just a pirate. Yeah. I guess my reading is he's just asking whether the tidal force as any effect on the post-ring down object? And if so, why should
Yeah,
that
so, I mean, certainly once the system if the system settles down into a neutron star, it may have some asymmetry, but it's sort of a different framework. So you can do perturbative analysis of an isolated neutron star and decompose the post-merger into a set of resonant modes that might be similar to the mode structure that you would use to analyze an in-spiral. But it's a sort of a different framework.
Okay. The next question is, what leads to two black holes or a black hole neutron star system to spiral towards each other? Is it only confined to binary stars?
Yeah, so certainly we know that it happens in binary stars, that two isolated binary stars like those we see in our galaxy so most of the neutron stars we observe in binaries that would eventually merge. That's sort of our main context prior to gravitational waves, but especially as we start seeing odder things, like these more massive systems, possibly with more mass ratios, we may begin to see clues that these did not form in so-called field binaries, but maybe come out of a capture process in a cluster of stars or something like that. So that's an interesting question for the populations of gravitational wave sources we hope to uncover.
The next question is there direct evidence for the post-merger to be a black hole? There is a proposal that the GRB jet may also be created for a massive neutron star.
Yes, so there's a few arguments that it's most likely that 170817 ended up as a black hole. They come from sort of analysis of the energy emission into the kilonova that was observed, and also they come from taking the gravitational waves that are favored by 170817 tend to have lower tidal parameters and thus smaller maximum masses, so that when you add the masses of the components together, it's most likely that the resulting object would have merged to a black hole. But there's no direct, there's no smoking gun that's necessarily what happened.
Okay. This may be a little out of your field, so if you want to pass, that's fine. But there's a YouTube question. Do we have quantum gravity effects when two neutron stars merge? And I don't quite understand the second part, but I guess if you have any comments about whether quantum gravity is important in these mergers.
Well, so fundamentally, we expect the dynamics here to be standard model physics. There's plenty of uncertainty with QCD to drive our physics puzzles. It's certainly possible that some sort of modified gravity or some quantum gravity effects that might produce effective fields that may, there are some alternative theories of gravity that can modify the effective structure of a neutron star, which might then in turn affect the orbits. The challenge is going to be decoupling that from our known unknowns of the equation of state uncertainty.
We have a couple more questions. This one is again from YouTube. Do mass ratios affect the inference on the equation of state and tidal parameters of the merging bodies? Are the fits improved through any consistency checks with post-merger observations?
Yes. yes, the mass ratios affect the equation of state inference. There's coupling between the parameters. Folks have done, I don't have them to hand, but I'd be happy to follow up by email or something like that. Folks have done, in a few ways, attempted to do a joint analysis on the equation of state using both the gravitational wave information and aspects of the electromagnetic observations. We don't yet have post-merger observations in gravitational waves directly. That would be another interesting thing. So far, the systematic uncertainties in mapping from the counterpart observations seem to swamp them making a large impact on the recovered equation of state information, but it's something people are trying to do.
Okay, and there's a follow-up to that question. Are there clear observable signatures that we are now aware of between binary black hole neutron star mergers versus binary neutron star mergers?
Unfortunately, nothing clear. Again, so you know, one of the things that people have debated is actually, could 170817 have actually been, say, a black hole neutron star binary with some particularly odd black hole mass? We don't know how a black hole of that mass would be formed. We don't necessarily expect it to. But if you just try and observationally rule that scenario out, it's surprisingly difficult to do. Even the kilonova, the light, the optical light can be compatible if you try to simulate a near equal mass black hole neutron star. It throws off a comparable amount of matter, and it has a similar final stage. So many of the observational signatures are similar in the two cases. So no clear signature, although people are working hard on trying to disentangle those two scenarios.
Okay. And the last question, it's probably related to the question a couple of questions ago, but if you want to say a little bit more, can you comment on the correlations among the equation of state dependent quantities in pre and post binary neutron star mergers?
So you can ask Paul about this in the next talk for sure. One thing that so certainly some of the overall pressure scales driven by the cold equation of state are going to be linked. So for example, if you're looking at the characteristic oscillation of the post-merger frequency, it's certainly correlated with the radius of a given mass neutron star. There's some work that shows that you want sort of a slightly higher effective mass to characterize the frequency of the post-merger. The post-merger will have somewhat higher densities, not as much higher as you might, I've sort of initially assumed. Also significant temperature. The time scale is rapid enough that you will start worrying about things like magnetic instabilities, neutrino effects, things like that. It's a more complicated system. I guess I'll leave my comments there because I think I'm running out of time. But I think you would definitely expect some of the baseline physics to be connected, and how the equation of state of slightly hotter and slightly denser matter will have something in common with the effectively cold and slightly lower dense matter in the same theoretical framework. but exactly how those are connected is certainly active area of research.
Okay, so yep, I think we'll close there. And thank you again, Jocelyn, for giving this talk, and we really appreciate it. Do you have anything to say regarding just, if students want to get more information, maybe through your website, maybe a quick plug for something?
There's a Gravitational-wave open science site. I really recommend that for students who are keen to learn more about gravitational waves. There's a bunch of folks in the LIGO and Virgo collaborations who put a lot of work into writing tutorials. There's workshops that you can see and work through Jupyter Python notebooks to try your hand at gravitational wave analysis. So that's actually somewhere I would point students who are really interested in learning more about how the gravitational wave science is done. And then the other thing that I didn't have a chance to talk about was something like was Cosmic Explorer. So that's sort of, for the students today, the cool instrument that may come, in a decade or 2 decades from now, that will see gravitational wave source background that tracks the structure of our universe.
Thank you.